Okay, in this video we'll talk about similar matrices. So here's the definition. Let's say that A and B are two n by n matrices, so square matrices with the same size. We say that A and B are similar if there is an invertible matrix P such that B equals PA P inverse. Well, one thing you notice is that this is closely related to the concept of a diagonalizable matrix. So the remark is the matrices that are similar to the matrices similar to diagonal matrices are precisely the diagonalizable matrices. Right, and we're talking about these can be either real matrices or complex matrices. So let's just say we have matrices with real coefficients. And so these would be diagonalizable over R, over the real numbers. The matrices that are similar to diagonal matrices. With real entries. Okay. So let's just look at an example. Let's say that you have a matrix 1, 2, 3, 4. Let's say that's A. How do we come up with a matrix that's similar to A? Well, you can just take P to be any matrix and then multiply PA P inverse. So if P is the matrix 1, 1, 2, 0, say, then P inverse is, let's see, the determinant of this is -1, so it's 1 over -1 is -1, and then times D, and then -C. Isn't that right? If you have A, B, C, D, then the determinant, then the inverse 1 over AD B minus BC times D -C -BA. Isn't that the correct formula? Yep. So you have a 0 here, and then -2 here, and then -1 here, and then 1 here. So P inverse is 0, 1, 2, -1. And then you can just calculate 1. I'm reading the numbers in different orders. The point is that you take P and then multiply it by A and then multiply it by P inverse, and then you get some matrix, and this matrix, let's call it B, this is similar to A. What if I have a matrix that's diagonal with the same entries on the diagonal? Well, in this case, no matter what P is, a PA is going to equal A times P. It's just going to be 2P. So that implies that PA P inverse is just A. So the only matrix similar to A, in this case, is just A. Okay, and it's, true, and if you just replace 2 with lambda, the same lambda, then PA and AP are both equal to lambda times P. So you can just replace the 2 by a lambda, and it'll still be true that the only matrix similar to A is A. Okay, let's make a little note. So first of all, if B is similar to A, okay. If okay, maybe we shouldn't state it like this. So we say that if A and B are similar, we say that A is similar to B and B is similar to A. Now, if B is equal to, there's one thing that I sort of overlooked, which is, so I'll make this a note, that if B is some matrix PA, P inverse, right, then A is going to be P inverse BP. So, and this is also a matrix times B times the matrix inverse, right? Because this is, if we let Q be P inverse, then then Q inverse is P, so this is Q times B times Q inverse. So this relationship of being similar is symmetric in the sense that if B is some invertible matrix times A times that matrix inverse, then A is some invertible matrix times B times the matrix inverse. Okay? Yeah, okay, so let's look at some properties of similar matrices. So similar matrices, we'll see that the significance of similar matrices is that they can represent the same linear transformation with respect to different bases. When you have a linear transformation and you pick 2 different bases, then you can represent those linear transformations with 2 different matrices, and those matrices will be similar. So that's a bit more advanced, but let's just continue working with this definition. I just wanted to point out that it is a natural definition. Okay, so the first statement is that similar matrices must have the same determinant. So the proof of this is, so suppose that A and B are similar matrices, then B is PA, P inverse for some invertible matrix, and then the determinant of B is the determinant of PA, P inverse, and this is equal to the determinant of P times the determinant of A times the determinant of P inverse, and then we've seen that the determinant of P inverse is 1 over the determinant of P. And since P is invertible, the determinant is non-zero, in case I don't have this issue of dividing by 0. So I have determinant of P times the determinant of A times 1 over the determinant of P. Determinant, in this case, are just real numbers, right? So I have a real number times 1 over that real number. I can cancel these, and I get the determinant of A. So therefore, indeed, B and A have the same determinant. The next statement is that they actually have the same characteristic polynomial. B and A have the same characteristic polynomial. If B and A are similar. Actually, this is a stronger statement than that they have the same determinant, because the determinant is what you get by plugging in 0 into the characteristic polynomial. So if they have the same characteristic polynomial, they have to have the same determinant. Okay, so how do we prove this? Well, the determinant of, so we have B is P times A times P inverse for some invertible matrix P. And the characteristic polynomial of B is precisely the determinant of B minus lambda I. And that's the determinant of PA P inverse minus lambda I. And this is equal to the determinant of PA P inverse. Now I'm trying to write this expression here as a product of matrices, so I can use my determinant facts. And the trick is that, so I notice that I have a P here and a P inverse here. Can I somehow get P and P inverse in here? And the answer is yes, because this is just P times lambda I times P inverse. Okay, because when you have lambda I, that times P is just, you can move the lambda out, right? And so this is equal to that, so then this is equal to determinant, and this expression on the inside, I can write it as P times A minus lambda I times P inverse by the distributive property of matrices. It might be a good idea to just multiply this out to check that that this works, right? Because you can multiply the P out and then you can distribute again, and when you do that, you're going to get the thing above. Okay, and now by our facts, as we've seen before, this is a determinant of A times the determinant of this matrix A minus lambda I times the determinant of P inverse, and then the determinant of P times the determinant of P inverse is just 1, so this is the determinant of A minus lambda I, which is precisely the characteristic polynomial of A. So therefore, the characteristic polynomial of B is the same as the characteristic polynomial of A. And in particular, that shows that they have the same eigenvalues. So a consequence of this is that similar matrices have the same eigenvalues. Once we think of similar matrices in terms of linear transformations, we'll see that this has a very natural explanation. Because B and A represent the same linear transformation, and eigenvalues are, so for eigenvectors, those are vectors that are scaled by a linear transformation. The eigenvalues are just how much the eigenvalues get scaled by. So if B and A are matrices that represent the same linear transformation, okay, since we're talking about one linear transformation, the eigenvalues of that transformation are the eigenvalues of A and B. That's basically the idea. Hopefully I'll make a video later explaining this in more detail. But anyway, the reason they have the same eigenvalues is because we've seen that B and A, so similar matrices, B and A have the same characteristic polynomial, and the eigenvalues are just the roots of the characteristic polynomial. There you go. And maybe I should have stated before that this theorem implies this proposition that similar matrices have the same determinant, right? It's the same argument except with lambda equals 0. But this is true just for any lambda. So this is actually a special case of the theorem below. So in fact, we didn't even have to prove this proposition and then the theorem. We could have just proven the theorem and then deduced that similar matrices have the same determinant. Yeah. And in the video on the trace, which is up, we show that, well, some of the things we sort of just assumed, but the theorem is that similar matrices have the same trace. That is, if you take the entries on the diagonal and add them up, you get the same number. And one proof of this is that we can view the trace as the sum of the eigenvalues, right? So the trace of A is the sum of the eigenvalues of A, the trace of B is the sum, and this is counting with multiplicity, the sum of the eigenvalues, and these include complex eigenvalues, of B, and now the eigenvalues of A are the same as the eigenvalues of B. So therefore, when you add them, you get the same sum. So that's the proof. And so what this means is, so similar matrices aren't necessarily the same matrix, of course, but they have the same trace, they have the same characteristic polynomial, and they have the same determinant. So what this implies is, if two matrices, right, if two square matrices have the same, have different determinants or different traces, then they cannot be similar. Or different eigenvalues, right? So, or different eigenvalues. They cannot be similar. On the other hand, you can have matrices with the same determinant, eigenvalues, and trace, but have them not be similar. So it can have matrices that with the same determinant, eigenvalues, and trace, but that are not similar. So an example of this would be to take A to be the 2 by 2 identity matrix and B to be this matrix, 1, 1, 0, 1. So what's the trace of A? The trace of A is 2, right? The trace of B is 2. The determinant of A is 1. The determinant of B is 1. And the eigenvalues of A and B are just 1 with multiplicity 2. And the eigenvalues of B are also just 1 with multiplicity 2. So you can have dissimilar matrices that are similar. I mean, not technically similar, but they're, intuitively similar by having the same determinant, eigenvalues, and trace. But they're not similar in the technical sense. Remember the definition? That there's no P inverse. Oh, well, I should actually prove there's no way we can write B as P times A times P inverse. Okay, so we've just shown that they have the same trace, determinant, and eigenvalues. How come they are not similar? Do you see why? Because we've just shown that the only matrix that's similar to A is the identity A, right? Because P inverse is just A. And in particular, it's not equal to B. So, So A and B are not similar. And it turns out that there is a complete answer to how to tell if two matrices are similar. For a 2 by 2 matrices, it's not so hard. But for n by n, it's still pretty hard. And it uses a theorem called the Jordan form. There's a statement called, there's a theorem that says that two matrices that are similar have to have what's called the same Jordan canonical form. And if they have different Jordan canonical forms, they're not similar. And so the Jordan canonical form is a way to distinguish matrices that are not similar. Okay, thanks for watching.